So we are live now. So you can
Yeah. So
we are live now.
okay, we didn't get any questions in the form.
So you can,
So if you have any questions in the YouTube window.
so we are live now.
Okay, we didn't get any questions in the form.
If anyone has any questions, just feel free to type them into the YouTube window.
Or if you have difficulty with any homework problems or anything of that sort or any concepts, this is your chance to ask.
Okay, maybe if there aren't any comments, maybe I'll just make one small comment about the stuff we were doing towards the end of the last couple of weeks, which is on trying to compute Galois groups and um, trying to see if a given Galois group occurs as the group of an extension and so on. So just a brief comment, and maybe we'll take more questions after that. So okay. So the comment I had was the following, that so we talked about the cyclotomic extensions and so on. So that those are what you get by so if you take Q and adjoin some primitive say nth root of unity, what we call zeta n's. So e to the 2 pi I by n. Then this extension was what we called a cyclotomic extension, and we had also worked out what its Galois group was over the rational numbers. So this is the Galois group was, well, you take the ring Z mod nz and then look at all the invertible elements, units in that ring. And this is, of course, an abelian group. In particular, we had looked at an instance of if you take n to be a prime number, then you use zeta p over q. The automorphism group is, well, it's the cyclic group of cardinality p minus 1. So this is dysmorphic to zp minus 1 because those are exactly, so z mod pz in this case is like the finite field, and this is just a set of units in the finite field. And the point here is that, therefore, what this shows is if you had a cyclic group of cardinality which looks like some prime number minus 1, then that group occurs as the Galois group of some Galois extension of Q. Okay? But more generally, so if you were to ask, so suppose I took Q and I wanted the following, I wanted an extension K such that the Galois group is a group G here. Okay, so I want this to be a Galois extension with group to be G. Then this is well, as yet unsolved problem in some sense. Given an arbitrary group, can you realize it as the Galois group of some Galois extension of Q? But at least what this cyclotomics that we talked about, what that says is that if G is a cyclic group of cardinality p minus 1, then you can solve this problem. We're just taking K to be the corresponding cyclotomic field. But also more generally, if suppose I had a cyclic group, more general cyclic groups. So if I take, say, G to be some cyclic group Zn, and I want to realize this cyclic group as the Galois group of some Galois extension, then the thing to do is more or less, start with the cyclotomics as your starting point. What you do is you choose some prime p. So choose some prime number p such that n divides p minus 1. So suppose you can do this, then what this means is that the cyclic group Zn, then how is it related to the cyclic group p minus 1? So observe that n divides p minus 1 was part of the assumption. So in fact, Zn occurs, you can think of it in two ways. The cyclic group of cardinality n is actually occurs as a subgroup, if you wish, of the cyclic group of cardinality p minus 1. Okay, so if you have a cyclic group, all subgroups are cyclic also. And if you have a number which divides the cardinality of your cyclic group, then there is surely a subgroup of that cardinality. But also, what else is true is that the subgroup also occurs as a quotient of ZP. So when I put this double arrow, I mean this is a quotient map. Why is this possible? Because you can also find a subgroup whose cardinality is p minus 1 divided by n. So that occurs as a subgroup of the cyclic group. And when you take the quotient, what you get is cyclic of cardinality n. Okay, so a cyclic group Zn occurs both as a sub and a quotient of the cyclic group Zp minus 1. So this the thing we talked about, the fundamental theorem of Galois theory and so on, what that then implies is the following. So if I have the cyclic, the extension Q zeta p over q. And suppose I have, so let H be the cyclic group. So take the cyclic group. So H is of cardinality p minus 1 divided by n. Suppose. Then, and so that the quotient, so if this is the full group, so Zp minus 1 is the Galois group of the entire extension. H is a certain subgroup, and by this the fundamental theorem of Galois theory and so on, there is a certain subfield between the Q, zeta p, and Q, whose associated group is exactly H. Okay, so this extension here, this is a Galois extension whose Galois group is isomorphic to H. So this is Galois group H. Okay, this is just the fundamental theorem. So this Galois group is the entire group Zp minus 1. And now interestingly, Zp minus 1 being cyclic, what it means is that any subgroup is normal. So in particular, we had the second part of the fundamental theorem. It said if H is normal, then something more also is true, which is that this extension on the bottom is also Galois. Not just that, we sort of know what its Galois group is. This Galois group here, so this extension here has Galois group, is isomorphic to the quotient Zp minus 1 over H. Okay, but that, as we just said, is we chose it so that it's isomorphic to the original group we had. Okay, so what this set of arguments shows is that if you have any cyclic group Zn, you can realize it as a sort of sub-extension, as a subfield of a suitable cyclotomic field by just choosing this prime number cleverly. Choose something which is of the form, such that p minus 1, n is a factor of p minus 1. Okay? And so, of course, there are many facts here that can always choose such a prime. And not just that, this argument here can be taken, again one step further. Not only can you do this if your original group is cyclic, you can also do this if you're given a product of cyclic groups. Okay? Sort of by the same kind of argument. Okay, so let me just point that out. So the same argument also works for not just Zn, but say something like this, Zn1 cross Zn2 cross dot. But then by the fundamental theorem of finite abelian groups that we covered in part 1 in algebra 1, this, any finite abelian group is always of this form. Okay? So we know that any finite direct product of cyclic groups. Yeah, so this basic idea of using cyclotomic extensions to construct, to realize a given cyclic group as the group of a Galois extension, you can push it forward. You can get the same sort of argument to realize any such group, direct product, as a Galois group. And since any finite abelian group is of that form, what we have shown is that any finite abelian group can be realized as the Galois group of some Galois extension of Q. Okay, so what's still open as of today is the general question for, not abelian. You take an arbitrary group G, not a abelian group, and then the question is, can you realize that as the Galois group of some extension? Okay. Just a comment about the last bit that we covered in weeks 5 and 6. So Poonam asks, did we cover normal series solvable group, finite abelian group in this course? So we haven't talked about solvable groups and so on. So in some sense that occurs, in this whole field of Galois theory, really. When you talk about the insolubility of the quintic. But what we have done, at least in the videos of this course, is to sort of bypass that general theory of solvability and so on, and instead, we've just given enough details to prove that there are insolvable quintiles. So to answer your question, no, we haven't covered solvable groups. Finite abelian groups were covered in the previous part in Algebra 1. So you may just want to refer back to the videos of the previous course. All of those videos are, by the way, freely available on YouTube right now through the NPTEL portal. So I mean through the NPTEL YouTube channel. So yeah. Any other questions? You had any difficulties with any of the assignment problems or any of the concepts we covered in class? Okay, Ashwini asks, what is radical? So I guess you have in mind this whole idea of this notion of radical extension that we kept talking about. So radical is just a name we give to things like square roots or cube roots and so on. So for instance, if you have, see, we have a quadratic equation, say x square plus bx plus c. Equal to 0, and trying to find the roots of this quadratic, then when you solve it, you automatically encounter square root. So we know that the roots look like this: b square minus 4c by 2. Right now, so similarly, when you try to solve, say, a cubic equation, you would sort of expect to get, say, you need to take things like cube root. So for example, if you just take x cubed minus 2 is 0. So of course the answer is, well, the roots are the cube root of 2. I mean, that's the real number whose cube is 2. Then of course the others are complex roots, cube root of 2 omega and cube root of 2 omega square. The notion of radical in general is, if you take, you're allowed to take any roots, nth roots, say fourth roots or fifth roots of things, in general nth root. So an expression like this, say fourth root of 2 minus, let's say, the seventh root of so 3 plus So 3 plus square root 2 plus 6 times is something like this. So maybe not even all the way, just a fourth root of this plus this and so on. So if I wrote something down like this, then you would say that this is an expression involving radicals. So radicals just means you take some nth power of some real number which you have obtained. So expression involving radicals. And so this appeared in in this whole insolvability of the quintic, the original problem that Galois tried to solve, which is that given a quadratic equation, we know we can solve it in this way using square roots or in general using radicals. So the question is, if you I mean, and it was also known that if you had a cubic equation or a fourth degree equation, they could all be solved in similar ways. You could write out an explicit formula using radicals, okay, meaning by involving various nth roots. So the corresponding question for fifth degree polynomials is the famous insolvability of the quintic. So what is a radical extension? A radical extension is something in which, so if I have a field F, a radical extension is one in which I adjoin to F a single element, something like this, F of alpha, where so what do you have? You want alpha to be some number such that some power of alpha power n is in F. Okay, so maybe if you call alpha power n as some number beta F, you can think of this as, so what are we doing here? We are adjoining the nth root of beta. So this is like saying I am adjoining the nth root of beta. Okay, so that is what the definition of radical extensions. You just adjoin a single nth root of some element which belongs to the base field. And what we talked about was, so this whole problem of trying to solve an equation by radicals is like saying, given, starting at Q, for example, can you construct a tower of radical extensions? So from Q, so the expression I wrote out earlier is like saying, okay, first I take cube root of 7. So I first construct that, say I construct this extension. And then, what did I do after that? I looked at 7th root of 3 plus square root 2, right? So I keep adjoining, a bunch of things like this. So it's like root of 7, and then I adjoin square root of 2, which is again, this is a radical extension because what I'm doing is I'm adjoining to the previous thing a square root of something which belongs to the previous term, right? So this is a tower of radical extensions. So what we looked at was to construct a tower of radical extensions. In a sense, it was parallel to this ruler and compass construction business, where you had to construct not a tower of radical extensions, but rather a tower of quadratic extensions. At every step, it had to be a degree 2 extension. So it's a completely parallel story when we talked about ruler and compass. So there you start with Q, and then you sort of, it's something of degree 2 over Q, something of degree 2 over K1, and so on. So this is every successive extension is a quadratic extension. So that is the ruler and compass situation. The general solvability using radical situation is to say, oh, can I start with Q and construct a sequence successive tower of radical extensions such that the root that I want, can I solve for all the roots of a given equation like that? So the alpha I'm looking for, the roots of the given polynomial, I want to find that alpha inside this, say the topmost field of this tower. Okay, so that's the broad context in which radical extensions. Now the point is, so what we did as part of the proof of this insolubility and so on is See, radical extensions are easy to understand or easy to work with if you assume that the base field has all the roots of unity. So for example, see if I have Q, and to Q I adjoin, say, the cube root of 2. Then, as we have seen in the examples, this is not a Galois extension, because cube root of 2 is only one of the roots of its minimal polynomial. The other two roots are cube root of 2 omega and cube root of 2 omega square. So this is not a Galois extension. But if you look not at this, but rather you first include all the cube roots of unity. So you put omega and omega squared into this. Say you take q of omega, then a further extension of that. So look at cube of omega of cube root of. Now this is a Galois extension. Okay, why? Because so now if you look at this, the other two roots are cube root of 2 omega and cube root of 2 omega square, and they are all there now in this field because you already assumed that omega is there. Okay, so the point with radical extensions is that they actually are nicely behaved if you assume that the underlying field already has roots of unity. Okay, and they also had some special properties. The Galois group of the radical extension was, so we had some nice properties. It had to be cyclic and so on and so forth. So not all algebraic extensions are going to be radical extensions. Okay, so these are a very special kind of extension, and that was really the crux of the proof. If you sort of looked at, which is sort of the Galois original argument really, which is that you cannot realize any root, for example, roots of certain fifth degree polynomials do not lie in a tower of radical extensions, because radical extensions are very special. Their Galois groups are very special. So by constructing so the crux there was to construct a polynomial whose splitting field had a rather complicated Galois group. You look for something whose Galois group was a symmetric group S5 or the alternating group A5. So when you have such a complicated, for the purposes of what Galois was trying to do, that is a complicated group, then you cannot realize that element via a tower of radical extensions. Because somehow radical is broadly speaking, it's like only having cyclic Galois groups. Yeah, I hope that's somewhat clear. Yeah, so Abdul asks about necklace problems. So we more or less did these in the previous. I mean, these were in Algebra 1. So maybe it's I would probably suggest that you take a look at some of those videos to get a better sense of these. So in fact, a few necklace problems were also solved as part of the the problem sessions that were part of the videos of each. Okay, Jaggu says, can you tell us precisely how we should get the intermediate fields of Q of square root of I over Q? So Q of square root of I, you mean the eighth root of unity, I suppose, Q of zeta 8. So this is the cyclotomic extension again. So this is zeta 8 is just, I mean, that's a square root of I, if you wish, pi I by 8. So here we know what the so it's a Galois extension. We know what the Galois group is. The Galois group is So you take Z mod HZ, the ring, and you only look at its units. Okay, so in this case, there are, well, what is this? The units of this ring, you can think of it as 1, 3, 5, and 7. So these are the units under multiplication. So this group is like saying, take these 4 numbers, mod 8 under multiplication mod 8. And that's the Klein 4 group, because, what is this? So this is Z, this is the Klein 4 group. Because every one of these elements, so firstly it's abelian, and every one of these elements, their square is identity. Because 3 square is 9, which is the same as 1. 5 square is 25, which is the same as 1 again, mod 8. Same with 7 square. So this is the Klein 4 group. And so the question now becomes, what is the, how does one find the intermediate fields? Right? So the intermediate fields are given by, the fundamental theorem of Galois theory, which tell you that you just have to look for the various subgroups of this group. And now what are the subgroups of the Klein 4 group? The proper subgroups. I mean, there's of course identity and the whole group. The proper subgroups are just the ones which are, there are, what are they? If you call these elements as, so there are 3 of them. So if you look at the cyclic group generated by 3, the cyclic group generated by 5, cyclic group generated by 7, they're all of order 2 each. And these groups are, so they are the subgroups of the proper subgroups of the Galois group. And each of them will have a certain fixed field. And that fixed field is going to be, that's going to give you all the possible intermediate fields. Okay. So in this case, if you take, for example, so how is this Galois group Z mod HZ? So let's look at this. So firstly, why is this Galois group? So Q of zeta A to Q. So what are the elements of the Galois group? There were 4 elements which we call 1, 3, 5, and 7. What are those 4? Really, the correct way to think about it is, you have zeta power 8, then there is zeta power 8 square, zeta power 8 cube, then zeta power 8, zeta 8 power 5, zeta 8 power 7. So look at these roots of unity on the circle, which are these 4 powers of zeta 8. Okay, that's square root of I. This is sort of I power 3 by 2, I power 5 by 2, and I power 7 by 2. Now, so there are now 4 elements in the Galois group. What are the 4 elements? What I call 1, 3, 5, and 7. Maybe we should call them by some slightly different names. So 1 is the identity, right? So one is identity. I'll call this sigma, tau, and this is in fact the product of sigma and tau. Okay. So let's look at what each of them has. Sigma is the map which takes, it's an element of the Galois group which is uniquely defined by this property that it takes zeta 8 to zeta 8 cubed. Tau is the fellow which takes zeta 8 to zeta 8 power 5. And sigma tau, the last one, is the map which takes zeta 8. This is the automorphism which takes zeta 8 to zeta 8 power 7. And the first case, the identity, that takes zeta 8 to zeta 8 itself. So here are the elements. Now what you have to do is figure out what the fixed fields are of each of these. Okay. So there are 3 subgroups. So let me call those subgroups as H1, which is the subgroup of sigma, which is 1 and sigma, identity and sigma. H2 is identity and tau. H3 is identity and sigma tau. And so the corresponding intermediate fields are just the fixed fields of these. So we just have to ask, okay, so let me give this a name. Let me call this K. Now ask, okay, what is K H1? In other words, what are the elements of Q zeta 8 which are fixed by by sigma really, right? So sigma is the map which sends zeta 8 to zeta 8 power 3, right? So it sends this guy to this guy, zeta 8 power 3. So what does it do to these other ones? So of course it maps 1 to itself, minus 1 to itself. So what does it do to I and minus I? I guess it sends, let's see, zeta 8. So I is zeta 8 squared. So zeta 8 squared will go to zeta 8 power 6. So which is minus I. Right? So this is the map which sends I to minus I. Okay. So what is the fixed field? Well, in this case, the fixed field is going to be, let's see. So first I should say it maps I to minus I. It maps 1 and minus 1 to themselves. And what does it do to these guys? It maps these two. Zeta 8 goes to zeta 8 power 3. Zeta 8 power 3 maps to zeta 8 again. Sorry, it's a little confused. So zeta 8 power 3 will map to zeta 8 power 9, which is zeta 8 again. So those two are switched, right? Okay, fine. So what is key H1? So what I know is that it certainly maps. So let's look at this. So zeta 8 plus zeta 8 cube. So I claim that KH1 is actually just Q adjoint zeta 8 plus zeta 8 cube. Okay. Why is that? Well, this is certainly fixed. If you notice, this element is fixed by sigma. So that's what it does. It exchanges these two. Okay. Similarly, it exchanges zeta 8 power 5 and 7. And then it maps I to minus I. It also exchanges the other fellow. I goes to minus I as well. So this element is fixed. But let's just see what this element is. Zeta 8 plus zeta 8 cube. So this is square root of I, right? So it's minus, sorry, this is 1 plus 1 plus I to 2 plus minus 1 plus I by 2. Okay, so those are the two guys written out in full. So that's just going to be 2i by root 2, which is root 2i. Okay, so this is just q of root 2i. So that's one of them. So similarly for the other one, so you'll have to see what the other elements do. Zeta 8 going to zeta 8 power 5. What does that do? It exchanges these two elements. Interchanges, swaps these two. Okay, and but then that's just the map. It sends everything to its negative. Yes. I mean, not everything to its negative. Yes. So these fellows to their negatives. And then I and minus I are sent to themselves. So you just have to see the action on the generator. So these two are sent to themselves. Okay, the others are interchanged. So in this case, for that second element, H2, again, we'll have to see what K of H2 does. So we have to ask, okay, what are the elements which are fixed by tau? And tau just does this. It maps this there. It exchanges those two and sends I to itself and so on. So here it is Q of I. Okay, so that's going to be the candidate. And then similarly for the other one. So we just have to see what that one does. It changes the other two guys, zeta 8 and zeta 8 power 7. So we do a similar analysis. What does that map do? It interchanges these two and these two. And sends I to I zeta 8 squared. 14, so that's this. So it also interchanges I with minus I. Okay, so here I guess the answer is KH3 is, so natural candidate is to just take zeta 8 plus zeta 8 power 7. and that's going to be by the same logic that we used before, 1 by root 2 plus 1 by root 2, that's q of root 2. Okay, so these are the, I mean, here I sort of just wrote out the candidates, but you can check that each of them is of the correct degree over Q. So remember the intermediate fields, we sort of know what the degrees are. See, we know that each of these fields, the total extension degree is 4, because that's the cardinality of Galois group. And each of these has to be a degree 2 extension. So each of this is degree 2, again by the fundamental theorem of Galois theory. Because the subgroups that we are looking at all have degree 2, right? I mean, all have cardinality 2. So that tells you that the corresponding fields that you have, they would have degree 2 when you think of it as, as sub-extensions of Q zeta. So what we have constructed are 3 fields. Okay, I mean, I've given you the candidates, but these must be the answers because you can check in each case that they are all quadratic extensions of Q. I mean, if this guy is degree 2, then so is this bottom is also 2. So you're looking for some appropriate quadratic extensions of Q, and we found 3 of them. So observe, this is a quadratic extension of Q. Right? This is like Q of square root minus 2. So this is just like adjoining the element minus 2 square root. Then there's Q root 2, and then there is Qi. Okay, so I hope that bit was clear. Okay, so there's also a question about cyclotomic polynomials. So those are, of course, we had an extended lecture on what their main properties were. So these are just the monic reducible polynomials satisfied by the primitive pth roots of, or in general nth roots of unity. So I could take zeta n e to the 2 pi I. And then the question is, what is the minimal degree monic polynomial rational coefficients with zeta n satisfies? And we had seen that polynomial, which was called phi n, and we just obtained as follows. We just take x minus, so it's, I mean, what are the other roots of that monic polynomial? They are just, so if you call it zeta n, this is just zeta n raised to, the various powers d, where d is relatively prime to n. So the GCD of d and n is 1. So like, for example, in the case of phi 8 that we just talked about, the 8th roots of unity, you have x minus zeta 8, and then its cube, 5th power, and 7th power. So this is the cyclotomic polynomial of phi sub 8. And we proved various facts about it, that if you just look at this, then it's always a monic, it's irreducible over the rational numbers. So those were the key facts. In general, phi n has degree equal to the Euler-Stoichern function phi of n. Okay.
I guess for prime powers, we had computed some cyclotomic polynomials earlier in the lecture.
Right.
Yeah. So in one of the earlier weeks.
Right.
And we
Yes.
used Eisenstein's criterion to show that it's irreducible. So I think that was done in.
Yeah.
It was done in week 2 in lecture 5, Eisenstein criterion. You can take a look at that. But in general, it's not so easy to write down the exact polynomial explicitly.
Yeah. So this question, Amri, you want to take the question on separable polynomial?
Actually, I guess there's no great advantage to so separability. In the essence, it means that the roots are distinct, and usually it's when you talk about extensions, it's only useful when you're talking about irreducible polynomials. Otherwise, you don't get a field extension. So I'm not sure what more to say. Do you have something more to say to that, Vishwanath?
Not really, yeah. So usually you only apply it in the irreducible case, at least. That's the. I don't see any particular reason to look at. I mean, you can always define it in general. I suppose there's no harm, but I think whenever you're using it, it's usually you're trying to apply it to an irreducible form. So that may explain the choice of why some authors tend to only define it in the reducible case. There's no great advantage per se.
But the thing is, irreducible polynomials are separable except in very strange kinds of fields. So a field is perfect if it's either characteristic 0 or it is of characteristic p, but the x goes to x power p is a bijection. And for such fields, it can be shown that every irreducible polynomial is separable. So maybe that's the other thing, why it's.
Swaroop has another question. If f and g are irreducible polynomials, which are separable with Galois group E and F over K, is Fg another separable polynomial? Can we, and if Fg is another separable polynomial, can we conclude anything about the Galois group of Fg? So I mean, okay, so this is so there are some general theorems of this kind which we didn't quite talk about during the course, but so for instance, if you have you say it's E and F are the two, let's call it these are, let's say, over Q, for example, separable over K. Okay. So there's this notion of the composite of these fields, which sort of occurred when we talked about the insolubility of the quintic and so on. So the composite of the fields is you assume that there is this big ambient field inside which all this is happening. For example, if K, the base field, is the rational numbers, you can imagine that E and F are all subfields of the complex numbers. Okay, so there's no loss of generality in doing this because you can always embed all your algebraic extensions into one given algebraic closure. And so the composite field is exactly what you are asking. So if if F and G, the splitting fields are E and F. So if this is the splitting field of F, the splitting field of G, it means that this contains all the roots of the polynomial F, that contains all the roots of the polynomial G, and EF is the smallest subfield which contains both E and F, the union of E and F. This will turn out to be the splitting field of the polynomial FG. Okay. And so your question is there something you can say about the Galois group of EF in terms of the two Galois groups here? Okay. So everything is a Galois extension, and you want to know if the big Galois group has some relation to these. And there are there's let me point out one such thing. So suppose E and F don't intersect. If E intersection F is K, then this big Galois group is just isomorphic to the product of the two Galois groups. Then the Galois group. EF, okay. Yeah, and if there is an intersection, you sort of have to correct it appropriately. But so this is one of the very useful sort of statements, that it's just a cross product of the Galois groups. So I hope that sort of answers your question. Can you conclude anything about the Galois group of Fg in terms of the Galois groups of F and G? So in this case, there is, for example, this cross product. Yeah, okay. Jagu says, if quintics can't be solved by radicals and the roots are not transcendental, then it must have some interesting decimal representation. I mean, there are some algebraic numbers, definitely. I mean, I don't know what you mean by interesting decimal representation. So there are some algebraic numbers typically irrational, and yeah, I don't know what further one can say in general. The nice thing with if you can solve it by radicals, somehow you have a proper hold on it. I mean, it's just trying to solve an equation in the most intuitive sense. You sort of manipulate it. You try to write it as some power of x equals something, then take square roots or the appropriate nth root, and then proceed and so on. So, I mean, this is partly motivated by how the cubic equation was solved. There was Cardano's formula and so on, where it's solved by this succession of radicals. I mean, it's being able to solve it by radicals is sort of one satisfying way to solve the equation, maybe. But like what Galois proved, it can't always be done. And for a quintic, in some sense, you just have to live with the fact that, okay, it's the roots are some algebraic numbers. It's just that you cannot bring them into this satisfying form of a succession of radicals. So that's the issue. I'm not sure about decimal representations. Anything to add there, Amri?
Not really, no. I don't know what decimal representations. It's something very tricky to put into this framework.
Okay. Any further questions or comments? Okay, maybe if there aren't any further questions, maybe we should bring the session to a close. It's almost time. Should we finish, Amri? Yeah. Okay, so maybe we will end this session now, and we'll probably have another such session somewhere further down the line. So please bring your questions there, and also feel free to just post on the forum, and anytime you have questions, no matter how silly they may seem to you, just feel free to do it. Yes. So there is Swarup finally says, yes, indeed, yes. Yeah, you're right. So there are lots of similarities in some sense between this whole Galois theory and the fundamental theorem covering spaces and so on. It's a formal, almost like a parallel theory in some sense. Yes, indeed. So it's a bit like Van Kampen's theorem. Yes.
In fact, there's a precise statement, right? The Galois group, fundamental group of spec K, something like that. Not something I want to get into here, but
Right.
in algebraic geometry, when you study schemes, you can actually view the Galois group as fundamental.
Okay, so maybe we'll call it a day, and thanks to all of those who came and asked questions. Okay, see you all. Bye.
Bye.